So here we are, finally, at the very end of the course, where we're learning about ecology. And the reason we put ecology at the end is because it's the culmination of everything else. We're taking all of that material you learned in Bio 101 and all the rest from Bio 102, and we're putting it all together now to talk about how this happens at a macro level, looking not just at what we started with last semester with the cell, but then how do those cells come together to form tissues? That's what we talked about this semester. Tissues form organs form organ systems form organisms. Awesome. Beginning of this semester, we talked about populations. We talked about how different groups of a single type of organism, a single species come together and reproduce. We predicted their various allelic frequencies from one generation to the next. And then we're moving now beyond that. We're not just looking at species, we're looking at communities, different types of species beginning to interact and control each other's populations. Just like we talked about with the endocrine system, there's regulating systems like negative feedback. There's going to be regulating systems within a community, within an ecosystem. So let's start with habitats. Where do these things live, right? So Earth's climate has a whole bunch of biomes in it. Biomes are sort of specialized areas with a specific amount of rainfall, a specific amount of light, and varied temperatures. There's all sorts of graphs I can show you. We're not going to go into individual biomes this semester. I think future Bio 102 students might, but for you guys, you're not going to. I want you to understand that broadly there are two big classes of biomes: terrestrial biomes and aquatic biomes. So we can divide up the Earth into the land and the sea. Terrestrial biomes, quite simply, are anything on dry land. Here we can see a tropical rainforest, but at the bottom, land. You're not underwater there. Terrestrial environments are highly impacted by sunlight. This is going to be a major determining factor in a terrestrial biome. Now, sunlight on the Earth is going to be different depending on where you are on the planet. Basically, if you're near the equator, here, sort of center of the Earth, if you were to slice it, you're going to be getting direct sunlight for a longer portion of the day. At either pole, you get more indirect sunlight. So that variation in the amount of sunlight means there's a lot of variation in the amount of energy at any given point on the Earth. The other thing that's going to impact terrestrial environments is going to be air circulation. And interestingly enough, that air circulation is going to be controlled heavily by sunlight because of heat, and then rising and falling air masses. So the way wind works, the way air currents work, is basically if you heat air up, it rises. Basically, I know, it's crazy. You heat air up, it expands and rises. And that's due to ideal gas law and all sorts of other things. When that hot air rises, cool air is going to move in from the sides and fill in the void where the hot air was. That means the air is moving. The easiest way I can put this is if you've been to the ocean. You'll notice that there's a breeze on the ocean, right? Like if you've experienced that breeze before. What's happening is during the day, you go out to the beach. What's the sand like? What? Did you say soft? Yeah, okay, I guess the sand could be considered soft if you like rocks. Hot is what I was going for, right? I don't know about you guys, but I come down, like I go to the beach and I'm the dad, so I have to carry everything. And I come down the stairs, I'm carrying all the stuff, and every freaking time I do this, I like take a step onto the sand, and I think to myself, I can handle this. This is fine. It's not fine. My brain knows it's not fine, but my feet are burning. So I take another step. Now I'm away from the safety of the stairs, heading toward whatever spot I'm going to. My feet are starting to burn bad. You've been there. Take another step, trying to act cool, and then at some point I just utterly give up and do that weird chicken run where you keep your feet off the ground as much as possible while carrying all the crap. The sand is hot. The air above the sand. Oh, yes, Carlos.
Why don't you get a beach cart?
Why don't I get a beach cart? I thought about that. I had a beach cart at one point. It has wheels on it. Turns out wheels don't work terribly well on sand.
Did you try to de-inflate them so that maybe
Have you tried to inflate the...
No, de-inflate them.
De-inflate the... No, they were plastic wheels. Yeah, no. Even big wheels, it's hard to...
Flip-flops.
Wear flip-flops? Yeah, that would be the way to go. But I always think to myself, I don't need flip-flops. I'm at the beach. I want to feel the sand on my toes. And that was...
Take your flip-flops off when you get to the
Look, I understand that 4 feet into the beach. But on the stairs, I'm not wearing flip-flops. Yes?
So in the senses lab, we covered that if you put your hand in the cold water and put it back in warm water, you'll think that the warm water is much hotter. Shouldn't we make sure to do the opposite as we stay around? Because I felt like cups of hot chocolate. I'm very worried that it gets hotter, but why does that happen?
So you're saying with adaptation, right?
Yeah.
Okay, so the question is, why are you not adapting to high temperatures like you would adapt to, say, cooler temperatures? The reason is because you're damaging yourself with high temperatures. So your body it's not going to get used to being damaged. Does that make sense? That would just, it's sort of it's a mental, your brain triggers and says, I'm still getting hurt, right? It's just like you're not going to stick your hand in a fire and leave it there thinking, this will be fine, except for that one dog on the comic. So it's another pathway your brain has to protect yourself. Yeah, no problem. Okay, so away from the beach, the big thing is sand is hot, right? Sand is hot, the air above the sand rises, the water is cooler. I run to the water to stick my feet in it as fast as I can because it's cooler. So during the day, air is moving from, I don't know why I'm leaning over the table like this. Air is going from the water, which is apparently right here, over the sand, and you have a constant inflow of wind. That's what happens at night. At night, what happens to the sand? It cools down very, very fast. But the water, which has a high specific heat, stays warm. So at some point during the day, you end up with no wind in either direction because the temperature of the sand and the temperature of the water is equal. But then the temperature of the sand goes down, the temperature of the water goes up, so the air above the water gets warmer. What happens to that air above the water? It's warmer water. It's warm over the water now. So it's warmer than the water, so the air rises. So now, from the land, you get a breeze coming out to sea. That's a small way that wind works. Looking at it at the macro scale. Warm, wet air rises from the equator, right along the center of the Earth. You're getting strikes, dead straight on sun. That excites the molecules in the water. It gets them warm, allows the air to rise. Now it is warm and it is wet. As it rises up, what happens to the temperature of that air? You're going higher and higher and higher, and that air is expanding out. Mm-hmm. Right, the temperature starts to go down. As it rises, it cools down, it condenses, rain. Make sense? All right, so you get a lot of rain in one area. So as that high, cool air dries off, you don't have water in it, it starts to descend because now it's cooled down. It's got no rain in it. All that water was lost right along the equator, which is why we have a lot of tropical rainforests along the equator. Now we've cooled down the air, it starts to drop down at 30 degrees north latitude and 30 degrees south latitude. At these areas, we have no rain. What do you expect Biome-wise, what do you expect from the environment at 30 degrees north and 30 degrees south? What's the land going to be like with no rain? Dry desert. And that's where you get some of the largest deserts in the world. All right, so we've dropped down at 30 degrees north. The air begins to warm up again at roughly 60 degrees latitude, 60 north, 60 south. You start to have warmer, not as warm as the equator, but still warm air rising, taking with it a lot of water. It rises and it cools down, so what's going to happen? Rain. 60 degrees north latitudes around Alaska. So you get a lot of rain. What happens when you get rain? You get a lot of plant growth. The largest rainforest currently, I know the largest rainforest in North America at least, one of the largest in the world is located in Alaska. Surprise, not a tropical rainforest, it's a temperate rainforest. But it has a lot of moss, it's got a lot of trees growing. All right, so you've risen. You've dropped all your water. It's now dry again. It's cooling down. What happens at the poles then? North and South Pole. Wet or dry? It's dry. It's very dry at the poles. Yes, there is still snow on the ground. That's people are like, but there's snow on the ground. Of course there is. It's freaking cold. It never melts. Well, now it is. But you end up with this next, at the poles, very little precipitation, and they lead to deserts, which is why, honestly, the Arctic and the Antarctic are considered deserts. They have very little actual snowfall, actual precipitation. So there we go. Going from the equator, we've got warm air rising and dropping water. As you move to 30 degrees, that warm air cools down and begins to sink because it gets more dense. As it sinks, it pushes the air away from it. So we have constant air circulation in the atmosphere. So you got that part so far? So get this. That's only talking in that vertical, the vertical space. Our planet spins. Surprise! We've got day and night. And due to the spin, plus those 30 degrees north, 30 degrees south rising and falling, you end up with what are called the trade winds. Basically, you've got a set of wind. Let's look at it from the bottom up. You got this blue line that's constantly blowing in an eastward direction. You go up about 30 degrees, and you get lines constantly blowing in a westerly direction. You go up again, and you're going to see in the westerly direction and then the easterly direction. Ancient sailing navigators used to use these winds to plot their journeys. Think about Darwin, right? Darwin basically went from England down Africa, and he's like, I'm going to then jump over to, so he went down to Africa, jumped over to South America following one set of winds, down the edge, all the way around, and then once, the reason that he ended up going by the Galapagos, because as you can see, that's where the wind direction changes. And then he was able to head farther off and toward the Indies, all the way back to Africa. You'll notice up here, this one spot that says 1, right? This spot right here, where you've got lots of circulation of the air, where you're going to have one cell interacting with another, and you get a turning. That's where hurricanes form. And as you know, hurricanes drop a lot of moisture. They pick up moisture from the water, they bring it over the land, and they drop all of that moisture. You don't see it here. Let's see if I can find it. Right down here, you see another one. This leads to cyclones, which are basically hurricanes. You have another issue over in the Pacific, but it's not as bad. So we have a lot going on with wind. Wind brings with it water. There are plenty of other influences on climate. Not just wind, not just sun of terrestrial biome. You also have seasons. Because you know what seasons are? We used to have those. Bodies of water. Mountains. Mountains especially. Seasons, as you guys have learned from, I don't know, early elementary school on, are caused by the tilt of the Earth in relation to the sun. It's not that we're so much farther away from the sun or not. It's as the sun orbits, as the Earth orbits the sun, it's wobbling back and forth. And that wobble takes roughly 365 days. As that's happening, we get varying levels of sunlight striking the Earth directly or indirectly. So here we can see the sun is striking the day side of the Earth. The Earth is tilted. So down here is getting direct sunlight. You know, southern hemisphere right now is getting direct sunlight. That's going to be summer for the southern hemisphere. Right now it's winter in the northern hemisphere, according to this image, because it's not getting as much direct light. You'll also note that at certain points of the year, basically the North Pole is entirely covered in darkness, and the South Pole has light all day and all night. I guess there's no real night. Another thing that severely impacts the terrestrial biome is going to be bodies of water. Water, as you guys learned from Bio 101, has a very, very, very high specific heat. That means that it's slow to warm up, but also very, very slow to cool down. Anywhere you have a body of water, you're going to have temperature stability. You guys think about a desert. Deserts have like no water, right? We can agree, deserts have no water. What is a desert like temperature-wise during the day? Extraordinarily hot. What's the temperature like at night? Extremely cold. Make sense? You go to a beach right next to a big body of water. The temperature during the day is a little bit warmer than at night, but there's not much more than a 5 to 10 degree fluctuation between night and day. The moisture in the air keeps the temperature stable. That is why most human civilizations evolved around a body of water. If you look at our ancient ancestors, say in the Indus Valley, there's always going to be a river close by, or a bay, or a lake. So bodies of water maintain stability in the terrestrial environment. Mountains also play an inordinately large effect on terrestrial biomes. The reason for that is they change weather patterns. Mountains will create what are called rain shadows. Basically, a moist, warm air mass will hit a mountain, and in order to get around the mountain, the air has to keep moving. Air is a fluid. It keeps moving. So it's going to hit that mountain and start to go up the mountain. As it goes up the mountain, what happens to the temperature? What happens to the temperature at the top of the mountain compared to the bottom? It gets colder. What happens to this warm, wet air as it gets colder? It condenses and it begins to rain. So one side of the mountain is going to get a lot of rain. As you get to the other side of the mountain, not so much rain anymore. This has impacted you directly, likely. A lot of you people probably grew up around here. Do you remember snow days? Those were awesome. And we would all always look out for a snow day. We'd watch that storm coming in from the Gulf, coming up through Alabama, thinking beyond reason, maybe this will drop a few inches of snow that will close schools. You guys have seen those storms before? I know you've had to have had the same hopes I have. It's come up. You've watched it drop. It's dropping like 10 inches of snow, 15 inches. There it is in Tennessee, dropping a ton of snow. It hits the Appalachian Mountains. You get a ton of snow out in Stanton. And then as it's going over the mountains, suddenly it turns to nothing. There's no rain, there's no slush, it's gone. Why? The mountains caused a rain shadow. Usually this works in the opposite way. Usually you get a storm coming in from the coast. So it's blowing in from Norfolk or something like that. It's moving in, it's going to hit the mountains, and it's going to go up or down following that mountain range. But they'll drop all the water on this side, meaning the other side of the mountains doesn't get much rain. So far, so good? Think about, yes? A lake effect? So a lake, this is usually a large lake. And we just saw this up in Buffalo, I think. What happens with lake effect snow is you get a lot of energy from the sun striking the lake. It puts a lot of moisture into the air right above the lake. If there's not much movement of wind, you've got a lot of moisture right over that lake, it will move very, very slowly over land. And as it's moving slowly, it's going to start to drop that precipitation. The slower it moves, the more precipitation drops in one spot. That's what they're going to call lake effect, if it's not coming in from the oceans. Most of our weather is primarily all that moisture is coming from the oceans, usually. But that's a great question. So yeah, mountains. Think about the Pacific coast. When you think of Oregon, you think of Washington, you think of trees, plenty of greenery. Following, there's a mountain range that runs right along the coast. Once you get onto the other side of that mountain range, desert, hardly any water. That's because of this rain shadow. So there we go. Questions or concerns? We've got a terrestrial environment, and we've got a water-based environment, aquatic. We haven't talked about aquatic yet. We're going to. Terrestrial habitats are usually going to be characterized by different levels of sunlight, different levels of rain, different temperatures, and how much wind they receive. Mountains and bodies of water will have a huge impact on the local conditions. So far, so good? Questions, concerns?